Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, recording just starting. So let's get the sound fixed up here. That's better, I think. Now, thank you all for coming. Not every course still has people in the lectures at this stage of the semester. So I'll finish off here today. Microphone is too loud. Go down a bit, that's better. I want to round out the treatment a little bit of non-classical logics, the alternatives to standard orthodox system, by just having a look at one or two things. I'll have a little bit of a look at how proofs go in some of the logics a little bit more than I did last week. I'll also show you technique, at least a partial technique, for demonstrating that certain things are unprovable. I mean, I say that we set up this logic so that we can avoid proving, some paradox of implication or something, but I didn't prove that, right? I mean, so look at that a little bit. And I'll also do some comparison between these systems to try and give you a flavor of what's provable in one, not provable in the other, and this kind of thing. Then there may even be time for a few concluding remarks, but I'm not sure about that. So let's just revert to where we were last week. So the idea was we had some logic to take account of relevance. The idea of that is that there's no vacuous discharge. And no way of emulating it by taking sneaky detours through conjunction or something like that. The point of that being to avoid a sequence in which you get a conclusion that's supposed to follow from premises that are not relevant to it. So, that's supposed to encapsulate the idea somehow that the assumptions were actually used in the appropriate sense in getting the conclusion before you're allowed to discharge them and pretend that it came from them. And then we also had a logic to deal with vagueness. Okay, and there the big deal was counting counting the uses of assumptions. Okay, so things get worse and worse as you stack up many appeals to an assumption. You can't just collapse them all to one. And then yesterday I talked about constructive logic, intuitionist logic, based on some kind of constructivist idea of truth, the idea, as I said yesterday, that the universe is a sort of work in progress, that we keep constructing bits of it, and that part of it is it's not it's not an investigation-independent reality that's kind of out there that we may or may not correctly describe. It's in part, at any rate, contributed by the use of the language that we bring to it, and that gave us our intuitionist logic. And a characteristic feature of that was that there's no double negation elimination. So proofs are have to be constructive. You can't show that something's true just by showing that it isn't false. Because you may be in a partial state of information, something like that. That was, the third of those was very easy from the natural deduction point of view. The other two involved making a distinction between two ways that we can put premises together for the sake of argument. And I symbolized those by two different kinds of punctuation. And, you know, these were tied to the logical rules. Connectives like and typically go with the comma, connectives like arrow and also negation go with this semicolon. All right, and then the point of that is that we can distinguish different structural rules. Okay. That gives a structure of proofs, things that we're allowed to do, how proofs are allowed to be sort of in the abstract, that depend on how things have been combined, on how the assumption numbers have been combined on the left-hand side if we're doing natural deduction in our standard sort of format. I went through this last week. I'm only going to do it very briefly now. But, you know, the idea there was that we don't care about the order in which things come. If we've got a couple of bunches x and y, we take x comma y to be essentially the same thing as y comma x. The motivating metaphor for this is set union, and it's as the algebraists say commutative, right? I mean, you can swap the order. Doesn't make any difference. And we have the same thing for semicolon. There, we're thinking of this as somehow x is applied to y in something like the way that you apply a function to its argument, but we're taking this in a you know, a commutative way as well. We don't care which was applied to which. They just sort of interact to get the conclusion. We could impose a stricter reading and we get a different logic, but we are going to take it in that sense. This thing is also, as they say, associative. So if we've got bunches like this put together, we don't care whether the x and y were combined and then z came along and got stuck on the end, or whether the y and z were combined and then x got stuck on the beginning. It's the same thing. We're just taken, you know, like a set. And these rules have always been present in the natural deduction system that we've learned right from week 2, except we didn't make them explicit there. We just sort of assumed them, right? Just used these principles as background. Here we're being really careful about these things, and we have the same things for semicolon as well. We don't care if these things stack up. We don't care in which order they came, or, you know, which was there first and which, you know, got stuck on later. So we have these structural rules, these basic structural rules for both of these operations. And then there are two other principles that are, you know, make an important difference between the two columns here. So one is weakening. If we've got a bunch, any old bunch of assumptions, and the bunch here may have commas, semicolons, anything inside it, and it's in some context or other, I'm going to break into Greek here and call that gamma. So gamma x is just some big bunch of assumptions in which x occurs somewhere as a sub-bunch. All right, it's just some context on the left-hand side. And if that entails a conclusion, then we can just weaken in any old junk we like in that same position, and we get the same conclusion, as long as we do that with a comma, because this is like a set, and what it means is you can choose whatever subset you need. It's like the data in a database. You can choose whatever subset you need to get your conclusion. So, of course, if you throw in more junk, it's still valid. And that's the whole basis of vacuous discharge in ordinary logic. Okay? That in any context, gamma, right, any bunch of stuff on the left where x occurs, you can weaken the sequent by putting more stuff with the x. Right? that's weakening. Right, and there's another principle of contraction, which I've referred to a few times, which says this, that if in this context you've got, so x twice, put together like that, then in the same context, you can just reduce it to 1. And that means repeating yourself isn't getting you any more and isn't changing anything, right? Just saying the same thing. Because x comma x is the same thing as x. So we have those for this comma, for the extensional sort of, this thing that we can kind of read like and, right? We have those principles. And obviously the same things hold for conjunction. For example, if something follows from A, it follows from A and B. If something follows from A and A, it follows from A. This is the thought here. Now, in the right-hand column, here for the semicolon, we have we can have as optional extras. We can have the analogues of these things. So weakening, if we get something from any bunch X, then we can get it from X semicolon Y. That's right. We want that in our in our sort of fuzzy logic, in the one for dealing with vagueness, right? So we'll call that, I don't know, system F or something for fuzzy. Right, so in the logic for vagueness, we do have that. In relevant logic, no, that's the bad guy. That's the bête noire, right? That's the thing that the beast that's responsible for all the paradoxes. So these logics disagree about whether to adopt that one. Conversely, in relevant logic, we have this, that if you need to appeal to some assumption twice, really in this putting it together sense, right? You need to apply something to itself to get a conclusion, then that just counts as getting it from X. Okay, you can apply any premise to itself, and that doesn't require any more work on the left-hand side. That's okay in relevant logic. In relevant logic, yes. In the fuzzy logic, no. That's the root of all evil. That's contraction. That's the thing that says if you've got all these 255 implications, right, then just by contracting you can pull them down, you can behave as if there were just one. Right? So the badness of making this inference with a lot of appeals to the assumption is the same as just using it once. Or if you take the conjunction of them all or something like that. And that's where we diagnose the Sorites paradox as stemming from that logical mistake. Right? So these two systems disagree about these extra structural rules. They each have one of them but not the other. Of course, there's another logic we could get in which we have neither of them, right? We say that both of those are bad things. That would be a smaller system. We couldn't prove as much. But it's still an interesting logic. I mean, it's still valuable and it's there and it can be investigated. There is one more thing that we need on this semicolon side. Now, the definition of a sequent is we've got one of these complicated bunches on the left, not just a set. It's not allowed to be empty on the left, so we need a special bunch, which I've been writing as a script L for logic, and that has the characteristic feature that what you get by applying logic to X is essentially just what you get from X. And we represent that in the natural deduction format, for writing out the proofs by assumption 0, which we never actually make. We could think of assumption 0 as the conjunction of all theorems or something like that, if we want to sort of have a concrete idea of it in our mind. So we've got these. That's just reminding you how the proof, how proof was defined for these two deviant systems. And we also know that how proof is defined for intuitionist logic, the third of these non-classical cases that we looked at. That's just ordinary classical proof, except we're not allowed double negation elimination, because it's not valid constructively. And we then have to put in a little bit of its effect, right, by throwing in an absurdity rule, which we can do by strengthening the negation elimination rule, say from A and not A you can infer B. Okay, so those are those three logics. Now, the next thing I want to do with these, make that a bit smaller, that's better. The next thing I want to do with these is look at a technique for showing that certain things are not provable from these, in these ways. And what I want to do there is slightly generalize what we do for ordinary classical logic, right? If we want to show that some sequence is not valid, one thing we could do is just search for a proof, you know, and after a while we don't find one, so we say, well, there isn't one then. But that's hardly convincing, right? I mean, that's maybe we just didn't look hard enough or long enough or we weren't creative enough or something like that. In order to show that a sequence isn't valid, you know, according to truth tables or something, we construct the interpretation that satisfies the premises and doesn't satisfy the conclusion. Right, and we say, look, that doesn't preserve truth in interpretation, so it's not valid. That's how, and then, you know, we use the fact that all of the rules of the system are sound for that interpretation, right? They all preserve validity. To say, so no matter what you do with the rules, you'll never be able to prove this one, right? Because you can't, you know, the rule of assumptions only introduces A entails A, which is valid on any interpretation, and all the rest of the rules preserve validity in the sense that if their inputs above the line are valid, then their output is valid as well, according to that kind of interpretation. So what we want to do here is the same kind of trick for these non-classical cases, except that of course we can't use ordinary truth tables and things, right? Because that won't do, right? If we want to show that you can't relevantly prove P and not P entails Q, it's no good using two-value classical truth table, because according to that, P and not P does entail Q, right? So that's not going to give us a counterexample. So we have to have some more general notion of what an interpretation is. Well, yesterday I actually gave you a definition of of one way of modeling intuitionist logic, right, by thinking of this set of states of information or something like that, and defining everything relative to those. And that works for that system, but I haven't done the same thing for the other two logics because it's too complicated, right? We'd need another month or something on the course to go through the model theory of these things in complete detail. But we can approximate it. And it's sort of useful to do that. You can do a lot, you can show a lot of things just with very crude approximations to the interpretation, to the semantic account of these logics. That's what I'm going to do now. So, in the very simple case for intuitionist logic, right, this thing will not stay the right size. Okay. So for intuitionist logic, we had a little account yesterday, just as a sort of three-valued story, on which we had, for instance, a table for conjunction that said, you know, things could be true, intermediate, or false, and A and B looks like that, and a similar thing for disjunction, and there's a story about negation, and story about implication, right? We can have these three values, and then we can use that structure in the same way as we use the two-value truth table for orthodox logic. And that is how implication works out. And negation, of course, there are just the three cases, true, I, or F, which turns out to be F, F, T. And that works. That gives us a little three-valued model of intuitionist logic. I want to keep it emphasizing, because people get the wrong idea, that intuitionist logic is not a three-valued logic, right? I mean, to do the thing accurately, you need an infinite-valued thing, right? But there's no way of reducing it to a finitely many-valued case. But even the three-valued one is not classical, and it enables us to make quite a few points about that logic. For example, we can argue that we can observe, just from looking at this, that not P isn't the same thing as P. And so double negation elimination isn't valid in this logic, because, well, what I haven't shown is that all the rules of the logic are valid on this three-valued interpretation, but they are. I mean, just sort of proof by method of confident assertion. Very useful proof method. So, all right, although this isn't a characteristic matrix for that logic, we can use it to establish a lot of properties. We can use it to show that certain things are not provable. And the fact that something is valid in this structure, it doesn't follow that it is provable, but the other way around is fine. Right? If something's invalid, then it's unprovable. Can we do the same sort of thing for the fuzzy logic? Keep calling it F. It isn't what's known in the literature as fuzzy logic. That's a special case. This is a slightly more general logic with better deduction theoretic properties. Right, it's got a proper natural deduction formulation, which the sort of stuff that gets called fuzzy logic in the literature, going back to Lotfi-Zadeh and people like that, that is proof theoretically, or from a deduction point of view, it's horrible because it's not set up to I mean, it's a different logic. But it's in the same ballpark, and so I'm going to call it this. We can have a three-value model of that, which looks superficially quite similar, although the reading of it is different, right? We can still call it the same thing, but read it differently. Here, the intermediate value means half-true, right? So we could call it H instead of I. Well, let's do that. Let's call it half. But it's still going to look broadly similar. These are going to be H, and the rest is going to be F. So we get the same table for conjunction. We get a different table for negation, right? True, halfway, and false. We get a different model here. These two are the same. But if P is half true, then not P is half true as well, because that's what half means, right? It sort of meets its own negation coming back the other way. So that's a slightly different table for negation, just in one point. And the table for implication is also slightly different. Again, much of it is the same. That line's the same. True, 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 true. The truths are in the same place. The only difference is in this place here, which is halfway. Right, if you go from half to false, you've descended by half a truth value. Right, that's the idea. So it's this kind of the reading of this values is just the distance between the two values, right? I mean, if you go down from true to half, you've gone halfway down the scale. If you go from half to false, you've gone halfway down. Right? The intuitionistic reading was very different. It was in terms of truth, which is yes or no, two-value truth at one one state of information and then the same thing at another state of information. So it's a completely different reading. But the tables are very similar except for just this one place here. And it's still the case that not A just means A implies false. The negation matrix is the right-hand column of this implication 1. Can we do the same thing for relevant logic? Well, yes, we can. We can get, again, there's no finite structure that's characteristic for it. Okay, it requires infinite ones in general, but even the small ones like 3 values can be useful. So the story here is a bit like the intuitionist story. We've got a sort of 2 places where we're evaluating truth. There's sort of ordinary here. The ordinary truth that we're interested in is the big one, right? This is sort of ordinary truth. This is the relevant model. Well, this is a model. It's a little cut down version. And then sort of inside it, there are some things that are super specially true, right? Or strongly true. Okay. And the way negation interacts with this, well, we'll see. I mean, there's sort of the reading of the 3 values now is quite different. So T now means strongly true, right? Being in this little middle bit. And F means being horribly false, being out here in the wasteland. And of course the intermediate one, which is being sort of slightly true, ordinarily true, right? Not super specially true, is being in the big truth. I mean, the more expanded general notion of truth. And the story here is that, well, this looks the same, as always. And disjunction, for all these things, disjunction is just the dual of conjunction. The implication matrix, though, is quite different. Here, well, if things that are super specially true are just implied by everything and absolute horrible falseness, not even slightly true, there's imply everything. And this guy is false like in classical logic. The other ones, though, it turns out here that if you're super specially true, you don't have any truck with anybody else. And the only place where, and for an implication to be just sort of generally true but not special, it has to be the case that both sides are in this case. Why? Just because that works, right? I mean, there is a story, but you can tell in virtue of this. You can work out from here what implication means, right? In order for the implication to be at least true, at least true in the weak sense of true. It has to be the case that it preserves, that the inference from A to B preserves strong truth and weak truth, right? It's the same as the intuitionist reading. In order for it to be true in the really strong sense, it has to be the case, well, then we'd sort of fall back on the more classical sort of story. It has to be the case that, either the consequent is strongly true, it's sort of super classically true sort of thing, or else the antecedent is strongly false. So it's like the not A or B, but with the extra sort of strength built in. And that gives us this matrix, and again, negation is the same as in the fuzzy case. And that's interesting from the relevant point of view, because the weak notion of truth is weak in the sense that a proposition can be true in that sense. That doesn't stop its negation being true in that sense as well. Right, so this little t is a fixed point for negation. And this gives us somewhere to park those things like P and not P if we don't want them to entail Q. Right? there's a weak sense in which we might want to accept both of them. So there we get some structures that are suitable for all three of these logics, and we can use these to refute some non-theorems. Okay, it's instructive to look at a few formulae here. For example, look at P and Q implies R and compare it with P implies that Q implies R. Classically, these two are the same. Right? If we can get... Oh, sorry. Yeah, P and Q implies R. Yeah?
In relative logic, why does the negation of false go to false?
Oh, sorry. Does it go to false? It doesn't. It goes to true, of course. Thanks. Thank you. Thanks for picking up that one. Yeah, of course. Of course. That's a T. Thank you. Yeah. So we can compare the fates of these two things. So these two are completely equivalent in intuitionist logic, because you can derive each from the other. You know, you could do this back in early stages of this course, right? I mean, this is week 2 stuff, right? You derive these from each other, and that doesn't involve double negation. It doesn't involve negation at all. So, since those are provable without any appeal to negation, classically they must be intuitionistically equivalent as well, and they are. But in the other two logics, they come apart. Okay, in the fuzzy logic, what happens here? Okay, well, suppose we I guess the case is where this only the case that fails here. In fuzzy logic, if the left-hand side holds, then the right-hand side holds, right? The left implies the right, but the converse is not the case. So it could be the case that this will have to get the middle value, and the other will have to get the false value. Yes. So if this is true, if P is true, I guess, true here, and we want Q implies R also to be true, but I guess that's true because P is halfway, Q is halfway, and R is halfway. Then the conjunction would be half, and R would be half. Oh no, that's not going to work. That's going to be true. I'm trying to construct this on the fly. There is going to be a counterexample, I assure you. How are we going to get? So how are we going to get this? We're going to get the left-hand side to come out as a half, and the right-hand side to come out as true, so that they're not equivalent. So half implies a half. Is that going to be half implies a half? And so is it going to be half implies false? Yes, that's going to be false. Okay, so they're one of each. So half implies false is a half. Half and a half is also a half. But half implies false, that's also half. But half implies a half, that's true. So in the fuzzy logic, these are not equivalent. The left-hand one could fail to be true if the right-hand one was true. So the thing on the right, this implicational form, if P then if Q then R, doesn't imply P and Q implies R, and that has to do with contraction. right, if we strengthen P to P and Q to P and Q, right, then what we'd be saying here on the right is that if we appeal to P and Q twice, we can get R. It does not follow that if we just appeal to P and Q once, we can get R. So, you know, this is sort of what we expect in terms of the fuzzy logic. In relevant logic, though, it's the other way around. These are still not equivalent, but now it's the left-hand one that doesn't imply the right-hand one. Okay, so we might be able to get from P and Q to R. It doesn't follow that in the context of P we got from Q to R. Q might have been irrelevant. Right, I mean, suppose R just follows from P. Right, then why would it follow from P that R follows from Q? I mean, Q is irrelevant. So this is what we sort of expect in relevant logic, and we should be able to refute this thing in the three-valued table. So we should be able to get the left-hand side to be, I guess, weakly true, and the right-hand side false. That means this has got to be true. Sorry, that means that. Sorry, I'm putting things in the wrong place. Sorry, this is the left-hand side. So that means that these both have to be weakly true. That fixes R. And for P and Q, I guess it's going to be one of them is true in the big sense and the other one's true in the little sense. No, that won't work. Yes, it will. So then this comes out as a true in the little sense, and that's big true, and that's little true. So little true implies little true is little true. And so the right-hand side comes out false, even though the left-hand side comes out true in the weak sense. Okay, so these logics are different. And, all right, intuitionistically, both of these directions here are provable. In the other logics, you know, one of them is going to fail. We have about 10 minutes left. Just wondering if it was worth. It probably is worth just showing you what one of these proofs looks like, because the proofs are slightly different in the different cases. So let's have a look at proving that one of these holds in one of these logics. So let's take relevant logic. That's sort of an interesting one. So we suppose that P and Q implies R. We assume that. Oh, this is the one that's going to fail. So there's going to be, all right, we'll do this proof in fuzzy logic and then observe why it won't hold in relevant logic. We assume P, it's a very classical thing to do. Assume Q. This is going to be proof in our system F. And we do the classical tricks, P and Q, 2 and 3. That gives us 2, 3. Right. And then we get R from 1, semicolon 2, 3. Right, that comes from 1 and 4 by just arrow elimination. Note that there's a semicolon there. Now what we want to do is peel off this Q and discharge the Q, say Q implies R. So in order to do that, what have we got? Right, well, we've got weakening, that's what we've got. How is that going to do the trick? we're going to have to weaken in some junk here. I see. Yes, we're going to do this inside here. So we're going to make this, we're going to make this in 2,3. Yeah, we want to make this 2 semicolon 3. Yes. Yes. I'm starting too close to this. It's a trivial proof. I can see it. Oh yes, of course. I'm an idiot. 2 semicolon 3, and we're going to do that twice. Okay, comma 2 semicolon 3. I haven't given myself enough space here. All right, so we just weaken. We just use weakening here. That still gives us R. Sorry, it's about the mess. That's from 5 weakening. And then that's got a comma in the middle, so we can contract on the comma. Right, that now gives us 1, 2, 3. Implies R. That's 6. And that's contraction for the comma, which is all right in all of these logics. And that's the same as 1, 2, 3, implies R. That's associativity, principle of semicolon. And then we can peel off the, all right, Q implies R from 8. Discharging 3, as usual. Arrow elimination, and P implies Q implies R, just leaving 1 from 9, discharging 2. Yeah, sorry about the hold up there. Just trying to do this in real time, standing close to it, couldn't see. Yeah, so this is how it goes, and of course this step here at line 6 is the one that's not going to be valid in the relevant logic if we try to do this. Relevantly, we won't be allowed that. Yeah. Oh, yes. I'm really making the I mean, what would be typos if I was typing here? Just rightos or something. Yeah, spelling mistakes, yeah. Of course, yeah, I mean, I lose a mark for that, but it's obviously just a slip. 9 out of 10. Okay, so you can see that in this kind of proof. What happens is a lot of mess on the left-hand side, not as much mess as there is on line 6 there, it's just because I didn't have enough space to write it. But you see that you've got to make all these moves to shuffle things around. You know, we had on line 5, we had this thing, but it got commas where we wanted semicolon, and then, you know, we want the 3 standing on its own on the right-hand side of a semicolon, and the rest, you know, so that we can apply arrow introduction at line 9. So in order to do that, we have to go through these, you know, intermediate moves. So, well, there are 2 weakening moves done in a row there together in line to get line 6, and that unifies these 2 sub-bunches, x and y, or it becomes x and x, and then we can contract them to 1 because there's a comma in between them, and that contraction's all right for the comma. And then we've got more or less what we want. We have to, you know, reassociate the parentheses and stuff like this. All those moves are there really in the orthodox standard classical proof that we learned right back in week 2. But we didn't do them explicitly. We just, you know, they just sort of elided into the use of the rules. And of course, if we're using a logic like this in anger to actually prove things, you know, for mathematical purposes or something like that, we'll do the same, right? We'll sort of adopt a principle that we don't care. We know that this semicolon thing is associative, so we won't actually write out two different lines there. We'll just write 1 semicolon 2 semicolon 3. Right? We won't put parentheses in. It's the same because we know it's the same thing. And we won't do the explicit contraction on the comma. We'll just weaken in the context and elide those rules. So we'd go pretty much straight from line 5 to line 8. We just say we can do those by the structural rules. But that's sort of how the proof goes. I haven't really got time to do the other direction, which will be relevantly valid, but not valid in the fuzzy logic because it involves contraction. Okay, I'm not sure whether these things are actually done in the course notes. There is a section where I refer to these things, and it's likely that if the proofs are not there, well, I'll put them there. So just worth noting the sort of things that we can prove and can't prove. In fuzzy logic, what we really importantly can't prove is things like if P then Q, if Q then R, therefore if P then R, with a comma on the left. Okay, so that's not in this fuzzy logic, and we don't want it because that's the bad inference that's involved in the Sorites paradox, right? The fact that that's not valid. And we can observe from the three-valued matrix that that's not valid. Right, with a comma. If we put a semicolon in that position, it's perfectly fine. Okay, but not with the comma. That one is relevantly okay. What we can't prove relevantly is things like P entails if Q then P and all that sort of stuff, right? In neither of these logics can we prove P and not P entails Q, so that's not in R, and that's not in either. But it is intuitionistically valid. In intuitionist logic we can prove this. Both of the other logics, the relevant and the fuzzy one, they both disallow this inference from P and not P to Q, but for completely different reasons. In relevant logic, it's because P and not P isn't relevant to Q. For example, they haven't got a variable in common, right? Haven't got a letter in common. In fuzzy logic, it's because P might be half true, in which case P and not P are both half true, but Q might be false, right? I mean, it's a completely different reason. So, yeah, some of those sorts of things. If we look at little proof, relevant proof of that, classical and fuzzy proof of the second of those, prove that P entails if Q then P, and see why does that fail relevantly to 1, 3, 1, 2. Suppose Q, so P and Q. So P, so if Q then P, from 4 discharging 2, spelt it right this time. Of course, that's a classical proof that makes it look as though, you know, P depended on Q because there was P on line 4 and there was Q among the assumptions. That can be reconstructed in the fuzzy logic. Of course, we have to go from line 4. We have to weaken in, we do the same thing, right? Weaken 1 and 2 and contract on the comma again. We can turn that comma into a semicolon, and then we're fine. But relevantly, we can't do that. Okay? In order to get if Q then P from P relevantly, we'd have to prove the sequent P semicolon Q entailed P, and that's not provable. We know that's not provable because we can refute it in this little three-value matrix. Right? Where is something that's yeah. So it's if P has this value T, little t, and Q is a big T, then